Okay, so we're going to leave the world of analog amplifiers behind, and we're going to jump and talk a little bit about digital logic gates. So time to get digital.
If you don't mind me asking, did you like these in order?
Yeah.
So we're on about 20, I guess?
We're on digital logic gates.
Yeah.
22.
You're down there.
22.
Yeah, right on, thanks.
Okay. So this is the part of the course where I'm going to be jumping around the book a little bit. I'm not going to necessarily go in the order that they're going. And so we're going to do some jumping back and forth and some rearranging of their curriculum, which, I don't know. It makes sense to me. It may not make sense to anyone else. But so digital logic gates, there's a whole chapter, chapter 5, on basic digital techniques. We're going to talk a little bit about chapter 5, then we're going to leave it behind and come back to it later. So the part we're going to talk about is basically on page 5-4, 5-5, basic logic gates, and a little bit on 5-6. And then we're going to kind of leave that chapter alone and move on to other things. So we're going to just very quickly go through digital logic gates. And in the early days, after the invention of the transistor, well, there was actually logic gates used with tube circuits, but you know, they were building size things, because tubes are physically large and they generate heat, and it's not necessarily the problem of running all those tubes, the problem of getting rid of all the heat and whatnot. So once transistors were invented and you know, the germanium and silicon structures were worked out and all that kind of stuff, people very quickly realized that, oh, we can make digital logic gates with these tiny little transistors instead of these big tubes, and you know, miniaturize digital logic as we know it. And of course that leads right up to today, where you know, your cell phone has over 4 million transistors in it. Yeah, it's about all. You know, and stuff like that. So really digital logic gates, so we're going to talk about them basically as a blob, but a digital logic gate could be as simple as one transistor, just hooking it up in different configuration. And in this case, we're using the transistor as a switch. It's either on or it's off. We're not using it as an amplifier or a mixer or all these other things we've been talking to it. It's effectively a switch. Digital is just that. It's on or off. It's a 1 or a 0, if you want to put it that way. Of course, digital talks in binary, 1s and 0s, binary meaning it only knows 2 numbers. It knows 1 or a 0. Or if you want to think of it in circuitry, an on or off. That's all it knows. It just can do those things very, very quickly, and an awful lot of them at the same time. So we're going to start with basic logic gates on page 5-5. They go through them really well. They start with the invert gate there, and the invert gate is just that. It inverts whatever you put in. If you put in a logic 1 in, it inverts it, so you get a logic 0 out, or vice versa. It inverts. In other words, whatever comes in, the opposite comes out. Simple as that. Once again, that can be a single transistor is a really good inverter, depending on how you hook it up. So the next one is the AND gate, and the AND gate has 2 inputs. It can actually have more than 2, but we're only going to talk about 2 inputs. And we just call the inputs A and B, input A and input B, and then it has an output. Output C is the way they labeled it in their little picture there in figure 5-4. And an AND gate basically means that both A and B have to be logic 1 for C to be a logic 1. In other words, A and B have to be high or 1 for C to be 1. Makes sense? And in other words, both things have to meet the condition, both have to and to meet the condition.
What's the little diagram there on the right?
That's called the truth table.
So, well, what is what? Because I don't see.
Yeah, that truth table kind of sucks because they don't really have C listed in there. Yeah.
Okay.
Well, there's 4 possible combinations, right? You can have both A and B or 0.
Mm-hmm.
You can have A as 1, B as 0. A is 0, B is 1, or both A and B 1. So you have 4 possible combinations. That little table they have there doesn't have 4 combinations.
Oh, I see.
So,
I think the horizontal is A and vertical is B all the way around.
yeah, and I don't know how they're doing. I'm ignoring those tables. So. In effect, so in an AND gate, just remember AND, A and B have to meet the condition for C to meet that same condition. So A and B have to be a 1 for C to be a 1. Okay. Next down is the OR gate, and the OR gate differs slightly that A or B can be a 1 and C will be a 1. Doesn't matter which. So A can be a 1, B can be a 1, and they can both be 1s, and C would be a 1. But if they both are 0, C is going to be 0. So, and or, right? So, or means any one of them or both of them. Okay? It's not an exclusive or, which we'll talk about shortly. It's just an or. So, one or the other or both 1, and the output will be 1. Then the next thing is we have a NAND gate. And all a NAND gate is an AND gate flipped on its head. So they just put an N, so like negative AND gate, NAND. So in an AND gate, we said that both A and B have to be 1 for C to be 1. Well, now it's flipped on its head. So both A and B have to be 0 for C to be 1. It's just an inverse. All we've done is flip it. We've added an inverter. We go back to the very first one. We've added an invert gate to our AND gate, and we call it a NAND gate. Okay. And likewise, on the bottom of that page is a NOR gate. And just like we talked about the OR gate, where one or the other had to be high, or both, this is the exact opposite. Now, one or the other has to be low for the thing to be low, or whatever. Once again, it's just inverted. It's flipped the crazy thing over. Okay. If we flip the page to page 5-6, there's something called an XOR, or an exclusive OR gate. And this is just an OR gate, but now one or the other has to meet the condition, in other words, a 1, but not both. So it's exclusive. Okay. Where the OR gate, either A can be 1 or B can be 1 or both can be 1, and puts out an exclusive OR gate. The condition where both are 1 does not make the cut anymore. Okay, so exclusively, in other words, they have to be different. They have to be exclusive. Okay, so there's an XOR gate or exclusive OR gate, and there's also an XNOR gate, which is just flipping the logic on its head. XOR and XNOR. Got all that?
Yeah.
Once again, we don't really care what's inside those gates. It could be as simple as 1 transistor. It could be as many as 12 transistors in there doing this flipping around. But we don't particularly care. For us, it's just a block. Okay? There's a bunch of pages the book goes through, and we're going to jump to page 5-8 and talk about a flip-flop. And that's not the thing you wear in the summertime on your feet. A flip-flop is a circuit, and it can actually just be made up of NAND gates, but a flip-flop is a device that has 2 or more stable states. So we can trigger this flip-flop, and the output will go from a 0 to a 1, and it'll stay there until you trigger again, and it'll flip back to a 0. So it's like a gate with memory, almost. And because it kind of has this memory, it'll maintain whatever state you last set it in. Another name for it is a latch. We can latch it into a certain condition, either a high or a low, and it will stay in that condition until we issue a reset to it to reset it back to its normal condition. Okay? So flip-flop, and another name for it is a latch. Another name for it is, you're going to love this one, a bistable multi-vibrator. Say what? A bistable multi-vibrator. How do you like that one, eh? Isn't that one so? So a flip-flop is probably the earliest form of memory, because it's a thing that we can say, I want you to be a 1, and it'll stay as a 1 until such time we come back to an A, either remove the power from it or issue it a reset back to 0. So you can almost think of it as a memory. It can be sitting off in the corner. You can have a dozen of these things and say, I want you to be 1, 1, 1, 0, 1, 1, and it will stay at that condition. It'll be latched, in other words, until such time as we come back and either read that back or we can reset them. So in the earliest stages of that, the flip-flops were a very early version of memory. And actually modern memory doesn't work a whole lot different nowadays. It's a hell of a lot faster, slightly different technique, but the fundamentals are there. That's all it is. Memory in your cell phone or your PC is just a location to say, we want to make you a 1, you a 0, you a 1, and you a 0, and just stay that way until they come back. That's all memory is, okay? In the most fundamental way. There's different ways of achieving it, but fundamentally it's all the same, okay? Yes, a bistable multi-vibrator or a latch, flip-flop. So in a multi-vibrator, which is a flip-flop, there's always 2 outputs in a flip-flop, by the way. There's the output and there's the output with a line drawn over it, which is the inverse. You can see a little schematic there on page 5-8. In figure 5-10, they show an RS flip-flop down at the bottom there, where it's got just a box, and on the left you see an R and an S, and the output you see a Q and a Q with a line over the top of it, or what they call a Q bar. Okay, the R and the S stands for set and reset. So if you put a signal onto the S, you set that latch, it flips, and it stays there until it gets a reset, an R. Okay, and the output is Q. Okay, and the inverse of the output is Q with a bar over it. So it's got 2 inputs, a set and a reset, or an RS. This is called an RS flip-flop. And all flip-flops, doesn't matter what variety they are, have that 2 output. You have the normal output, or the Q, and the inverted output, 1. So how do those outputs work? How do we achieve the Q and the Q bar? And basically, they're 2 transistors. One transistor is switched on, the other transistor is not switched on. That's what the outputs are. So you can imagine inside this box there's a number of transistors, but on that Q and Q bar, Q is a transistor, Q bar is also a transistor. One of those transistors is turned on, in other words it's switched on, so it's conducting electricity, and when it's switched on it would probably be a logic 0. The other one would be switched off, it would be a logic 1. There's your Q and Q bar, and you simply flip that state to flip them. Because one of the questions is, how is the output achieved in a multi-vibrator circuit? And the answer is, one transistor is turned on and the other is turned off. Oh my God, yes. In the, under flip-flops there on page 5.8, in the second paragraph, I think it's the second sentence, it says, what this means is that when output is a logical 1, the output transistor is cut off. When the logic is 0, the transistor is saturated and the voltage across it is near 0. So they actually tell you in there about this transistor thing.
Where do I read that? Say that again?
Second paragraph under 5-10, second sentence. It says what this means is...
Oh, the third sentence.
Yeah.
Okay. Yeah.
Or third, is it the third sentence or the second?
Well,
Yeah.
third line.
Third line, okay, yeah. 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 So, flip-flop, multi-vibrator. What was that other fancy name that I had for it? Bistable multi-vibrator. Latch. All talking about the same circuit. And in the end, it's really a very, very simple version of digital memory. And like I say, believe it or not, to this day, memories work on the same principles. Okay? So that's it. You're all digital experts. We're moving on. There's quite a bit more to that digital chapter, but that should tell you something.
Everybody thought digital was DMR and
Yeah. Okay.
This here's the basics of it.
Yeah. The next thing we're going to do is once again, I'm going to be jumping around here a little bit in the book, going backs and forths and backs. And we're going to go into chapter 7, specifically page 7-2. And we're going to start to talk about oscillators, but the first thing we need to do is kind of define an oscillator and what it is. And we talked earlier about an amplifier and feedback, and when you have positive feedback, an amplifier turns into an oscillator. But if all you do is you take the positive feedback, the output of an amplifier, and feed it back into the non-inverting input, it's going to oscillate, but at what frequency? Well, it's going to oscillate as fast as it can frickin' go. It depends on capacitance and inductance of your wiring and interstage, stuff like that. But if in that feedback path we put a frequency determining element, in other words, a coil and a capacitor, we can actually pick the frequency we want this thing to oscillate at. Okay? That kind of makes sense? So the frequency determining element that is used right up to today is crystals. And crystals are, piezoelectric effect? What a crystal is it's a piece of quartz that's shaved very, very thin, and it has a mechanical resonance. If you drop it on a table, it rings. However, it can ring at HF frequencies, at tens of megahertz or even hundreds of megahertz. And the neat thing is if you take this piece of crystal and you attach a wire to each side of it and you bend it, it will actually generate a voltage, which is cool. And likewise, if you put a voltage back on that crystal, it will physically bend itself. It has this weird mechanical bending stretch. Now, we're not talking bending a lot. You're not going to see it with the naked eye. It's a very, very small bend, but it does physically move. So if you shave this crystal down so its physical size gives it a mechanical resonance at a desired frequency, it turns out that the thing will vibrate very, very accurately and hold that over quite a wide range of temperature and humidity variations and all that kind of stuff. It turns out to be a very good frequency determining element for us, and they're used right up to this day in all our digital devices and stuff. All the internal clocks, we call them, the internal oscillators, are all crystal-based oscillators. This piezoelectric effect, they call it, is the effect of where if you mechanically deform this crystal, they generate a voltage. And the opposite works. If you put a voltage across them, they will mechanically deform themselves. They will bend. Okay. What this comes out of, we're going to forget about the mechanical aspects of it. It is mechanical. It is physically moving, but a lot of times we forget about that. What that looks like from an electronics point of view is it looks like a good old LC circuit. Remember when I drew the C in series with the L, and we determined that gave us a really nice bandpass filter? But if you just use a regular capacitor and a regular coil, it gives you a pretty lousy filter. It's very, very wide. Well, a crystal is a very, very high Q LC circuit. It gives you a really good sharp response right on its resonant frequency. Its resonant frequency happens to be mechanical. So, but as electronics guys, we just kind of forget about the mechanical part. We know it's happening, but we can treat it as if it's an LC network. Okay. So typically we take an amplifier like an op amp, and in the positive feedback loop we just stick a crystal in there, and all of a sudden our oscillation is going to happen at the frequency of that crystal. And it's very, very accurate and very well controlled. And if we want to control it even more, we can put that crystal into a temperature controlled environment, i.e. a little heating oven and stuff that heats it up to a certain temperature and keeps it quite stable in there. And yeah, you can buy little crystal ovens, a little tiny oven that this crystal sits inside, and it's soldered right inside your radio. And that is called an OCXO, an oven compensated crystal oscillator.
So it'll change the temperature then?
Yes, it does change with temperature. Remember, this is a physical piece of quartz, so everything expands and contracts with temperature. So if it expands, its frequency is going to change ever so slightly, right? But if you can put it into an environment where the temperature is stable, well, now you're talking pretty stable oscillator, right? So there's a number of ways to do it. You can have just a raw crystal that sits there going up and down in temperature with whatever the room or the environment is doing and varying in frequency, and that might be good enough. That's not good enough for all of our digital modes, even on HF. We need to go something to what they call a TCXO, a temperature compensated crystal oscillator. And what a TCXO is, it's a crystal, but the manufacturer has taken that crystal and has plugged it into a test jig and has varied the temperature over a wide range and has actually kept track. Okay, at this temperature, it's 10 hertz high. At this temperature, it's 12 hertz high. And they've built a correction chart, if you will, to know that, okay, when the crystal's at 25 degrees C, it's right on frequency. At 30 degrees C, it's going to be 10 hertz high. And they build that into what they call a TCXO, a temperature compensated crystal oscillator, and they program that into the radio. So when you tune your dial and the thing goes, oh, it's 30 degrees C in here, I know I need to subtract 12 hertz from the crystal to be right on frequency. So that's TCXO. Okay, and most of the, shall we say, the modern HF rigs that we buy now come with TCXOs automatically. It's built in, it's programmed into the radio. We didn't think about it. You just dial up and you're on frequency. If you want that dead-eye laboratory grade accuracy, you got to go to an oven compensated, an OCXO, and that's where there's actually a little temperature chamber in there that keeps the crystal at that exact temperature, and then those things are deadly accurate, and they'd be deadly accurate for 30 plus years. Because really, this crystal is just a hunk of quartz. It's a hunk of rock. You know, it ages very well. Okay. So it looks like a very, very high Q tuned circuit, LC circuit. With that, way back in, just where we could dance around, way back in chapter 1, on page 1-23, remember we were talking about filters and the L's and the C's, and then we talked a little bit about cavity filters and comb filters. Well, the one thing I skipped over was crystal filters. So I'm just going to jump very quickly back to page 1-23 where they're talking about crystal lattice filters. And so instead of using an actual coil and an actual capacitor, we can take crystals at appropriate frequencies. And you can have one crystal if that's all you need, but you can have multiple crystals hooked up in multiple configurations to make any size, shape, and configuration of a filter you want. Isn't that cool? Okay, because a crystal is the equivalent of a really high Q, L, and C. Really good example of this is on our HM on our 2-meter repeater on 14706. The receive side of that is 14646 because it's 600 kilohertz low. We have a crystal filter connected to that repeater on 14646 to filter out everything except 14646. Very, very sharp filter. That thing doesn't need any other filtering at all. That thing works a charm. Problem is the loss. Loss through those filters is massive. It's like 10 S units if you want to put it on an S meter scale. So we have to add a preamplifier to make up for that crystal filter loss. So you don't get something for nothing. They make a wonderful filter, but they lose a lot of the signal. Okay.
Okay, so that compared to the cans, if you're using the cans, which is the it's replacing, is that right?
Yeah, we found that actually using 2 large cans and wiring them up in series is the same, actually a little bit better than the crystal filter, but it only gives 1 S unit loss.
Right.
As opposed to about 10 S units loss.
Yeah, okay, so
but the problem is these cans are big and they take a lot of room, where this crystal filter is just a little box. with an
Yeah.
RF connector on it. So everything's a trade-off,
That's
right?
Okay.
You don't get something for nothing. Let's just put it
Are
that way.
these crystallized filters, how are they from a price point?
Very expensive. Because every one of these crystals has to be basically hand-picked and
Yeah.
frequency chosen and stuff like that. They're stupidly expensive. Okay. But like I say, going back to filters, I just throw that in there. Like I say, we're dancing around the book here a little bit. The shape of that crystal filter is determined by the combination of the crystals in it. It may only be one crystal. If it's one crystal, you're going to get a simple bandpass, very sharp bandpass. But if you want to pass, maybe a couple of megahertz, you're going to have multiple crystals in there, and they're going to be tuned to different frequencies, overlapping and stuff. So the pass band or the shape of that filter is going to be determined by the number of crystals and how they're hooked up inside there. And the bandwidth of those filters are really popular place for crystal filters is you buy an HF rig and it has these optional filters you can install. For $350 you can buy a single sideband filter, and you open the radio and you plug this thing in, and it is a crystal filter. And for single sideband, the bandwidth of the filter is how wide? It's about 2.1, 2.2 kilohertz, something like that. That's the single sideband. The CW crystal would be like 500 hertz wide. So once again, it's a very, very narrow, sharp bandpass. So if you just want to listen to the 500 hertz width where your CW signal is and it reject everything else, crystal filters are the cat's meow.
That's what those are for, right?
Yeah, that's what those are for. And yeah, the radio manufacturers charge lots of money for them because they are expensive. They are basically, they're pretty much hand-tuned. It's a high labor process to make them. Thank God for digital signal processing. We don't need them in modern radios, but in older radios, that was all the rage. In the old days, you bought an HF rig, and then you bought the crystal filters for it if you wanted them. They had options where you can, and some of them, like I know the Kenwoods, they had options for 2 or 3 filters in various stages. So if you wanted to option this thing out, you were buying 7 or 8 filters at about $300 a pop, which cost more than the original HF rig did. Okay, so, but that's where these guys come from. Like I say, the advantage to them is they're very, very high Q. The disadvantage is, of course, they're expensive and they're lossy. So you don't get something for nothing. Isn't that amazing? The other thing about crystals, we treat them as an LC circuit. Always got to keep in mind they're in fact a mechanical thing. At high frequencies, the higher in frequencies you go, the smaller this tiny, tiny, tiny little sliver of crystal is. It's mechanical. The smaller it is, the faster it can vibrate. The bigger it is, it's got more mass to move, so the slower it's going to vibrate. Because we're counting on a mechanical vibration, in the case of high frequency ones, a tiny, tiny little microscopic sliver for a vibration, the actual amount of power, if you will, that they can produce is minimal. They're a very, very low power device. So even in the feedback of an amplifier circuit, you're not going to get a lot of signal out. So typically what happens is a crystal oscillator circuit is usually it could be a FET or a transistor or even a modern op-amp with a crystal in a positive feedback configuration. It will sit there and it will be isolated all on its own, and then you will have some amplification stages after that, because that crystal puts out minuscule amounts of power. It likes to sit in its own little world, dumb, fat, and happy, oscillating away. If you try and load it down, for example, hook it up to an antenna and transmit with it, chances are it'll stop oscillating. Because we always got to keep in mind it's actually a mechanical vibration that's happening, and if you add too much damping to a mechanical vibration, well, it stops. So it likes to be off on its own. So in most radio designs, and right up to the modern ones, you'll see a crystal oscillator, but right after that you will see, it might be a low gain amplifier, but they call it a buffer amplifier. And that buffer means we want that crystal to be happily operating in its own little world, not being, bothered by all the other circuitry in our radio. So we put a buffer amplifier that takes that crystal frequency, amplifies it up a little bit, and that amplifier has capability to put out enough power to drive all our mixers and other circuits that we need to further down the line. So that's about it for crystals, except for one last thing before we talk more generally about oscillators. Crystals, it's a mechanical vibration, once again, and we tend to forget that, but you don't forget that the first time you start playing with one. And you get it to oscillate, and you realize that, well, hang on, this crystal is cut for 1 megahertz, but my circuit's oscillating at 3 megahertz. What the hell's going on here? The neat thing about crystals, because it's a mechanical vibration, is it can actually achieve vibration on a harmonic, on a multiple of its fundamental frequency. So a crystal that's cut to 1 megahertz will actually oscillate quite well at 3 megahertz, or even 5 megahertz, or even 7 megahertz. Much above the 7th harmonic, they tend to fall apart. So a lot of times, the crystals are running actually on a harmonic of their fundamental frequency, not on the base frequency of the crystal. And it's up to us, working in the RF circuitry, to be aware of that. The reason they do that is it's much easier, by the way, to make a low frequency crystal than a high one, just because it's physically bigger, and things that are bigger are easier to work with and easier to shape and form and package and all that, as opposed to microscopic tiny slivers of stuff. So a lot of times the crystal may be marked as, say, a 1 megahertz crystal, but the oscillator might be putting out 5 megahertz. We're actually running on the 5th harmonic of the crystal, and it works just fine. Okay? So the name for that is a harmonic oscillator, or another old-fashioned name for it, which you may hear, is an overtone oscillator. Yeah, another one of those industry Canada terms, an overtone oscillator. Don't you like it? So an overtone oscillator is a crystal oscillator running on one of its harmonics rather than on the fundamental frequency. And I say it can be very misleading, because when you buy a crystal, usually stamped on the package, it has the fundamental frequency. So if you buy, say, a 1 megahertz crystal, it'll say 1 megahertz on it. You put it in your circuit and it's oscillating at 3 megahertz, and you're going, oh, they sold me the wrong crystal. Well, no, they didn't. It just happens that you managed to pick a harmonic, okay? So instead of talking specifically about crystals now, we're going to kind of back this whole discussion up and talk generally about oscillators. And so that means we're going back to chapter 7 in the book, and we're going to start at around page 7-2. And first off, the definition of an oscillator is simply an amplifier with positive feedback. Okay? And I think we got a little bit of a handle on that. If we put a frequency determining element in that positive feedback path, we can actually pick what frequency we want our oscillator to work on. And in the RF world, that's a good thing. Everybody run out and build your 630 kilohertz transmitters right now. Back in the early days, a bunch of engineers and researchers started looking at these oscillators and designing different oscillators. And one of the first oscillators was designed by some guy of the last name of Pierce, and it's called a Pierce oscillator. And on the bottom of 7-2 and the top of 7-3, they talk about the Pierce oscillator. And they actually have a schematic diagram of a Pierce oscillator up on the top of page 7-3. Now, the amplifying element they're using here is a FET. It could be a transistor, it could be a FET, it could be an op-amp. FETs are used because, once again, crystals are not a high-power device. Crystals can't produce all kinds of energy. And the FET, remember, the gate of that FET requires almost nothing in the way of current to operate the device. FET is a very, very high impedance input. So crystals like FETs, because FETs are almost invisible to them. Crystal wants to sit in its own little world. So the positive feedback path is pretty obvious here. You can you can see the drain of the FET is fed directly back to the gate. That's your positive feedback path with the crystal in the middle. So the crystal is going to be the frequency determining element of this oscillator. And the crystal, notice, also has a little capacitor going to ground there, a series capacitor. Isn't that fun? So that's Mr. Pierce. He's fun. Next off is Mr. Colpitts, the next one down on page 7-3. Once again, we're using a FET as the amplifying device, and our positive feedback comes through.
Source.
It comes through the source, but through what path? So from the source, it goes to those two capacitors, C1 and C2. Okay, and it goes through those back through the crystal, through the gate. Notice there's a little variable capacitor put in series with the crystal there, and that lets you fine-tune the crystal to get it smack on the frequency you want. Okay? So the Colpitts oscillator uses that split capacitor, they call it a split capacitive divider, to achieve the feedback path. Really the difference in these circuits is how the feedback path works. They all have positive feedback, it's just every one decides that this one is better than the other one. At the bottom of page 7-3 is the overtone oscillator, and this is where we're going to run the crystal on one of its harmonics. And so once again, we're using a FET in the feedback circuit, much like we did back with the Pierce oscillator. But this time, we have a variable coil and a capacitor up there, and that's what's letting us pick the harmonic we're interested in. Whether it's the third harmonic or the fifth harmonic or the second harmonic of the crystal. Isn't that just the most lovely thing you've ever seen?
Crystal doesn't vibrate on its own, it needs power, doesn't it?
Yes, it needs power. So, the last one is on next page 7-4 down at the bottom is something called the Hartley oscillator. And the Hartley oscillator, once again, it's just the difference in how the positive feedback is done. If you look at the Hartley oscillator in the bottom of 7-4 there, figure 7-5, the Hartley oscillator, the positive feedback now goes through a pair of coils, or a tapped inductive feedback loop, through the crystal. The crystal isn't really labeled there, but the crystal is in line with the gate of the FET, and through there. So isn't that just the most fun?
So where is crystal?
The crystal is, it looks like a capacitor. They didn't label it.
Oh.
That symbol that looks like a capacitor, that's the crystal.
Oh.
On the
Yeah.
output side,
On the gate side,
little
yeah.
typo there, I guess.
Yeah.
Sorry for it. Must be that one.
You're talking about on the left-hand side, right?
Yeah, on figure 7-5.
Before the MOSFET.
Yep, just before the FET, that capacitor, that's actually the crystal.
Feeding into it.
Yeah. They didn't do
They didn't do
a good job writing that one up at all, did they? Yeah.
And that's why they brought out a third edition.
Yeah. Yeah, the third edition probably has that correction.
Check
Yeah,
it.
so
They
that's
did
it,
a
so.
good job.
So the kind of questions on the exam are, a distinct feature of the Pierce oscillator is the feedback is blank, capacitively coupled. The distinct feature of the Colpitts oscillator is the feedback loop is capacitive divider. A distinct feature of the Hartley oscillator is the feedback loop is a tapped coil or tapped inductors. Okay, so that's the kind of thing that's on the exam. It's basically, it's just to make you aware that all these use positive feedback. It's how that positive feedback thing is achieved. Some of these are better for things than others, and the Colpitts oscillator, which was, I think, the second one they talked about, turns out to probably be the most stable design.
Go
And,
back to Pierce oscillator for a second.
sure,
You said that you're talking about what was on the test there is feedback coupling is capacitive, correct?
yeah, it's capacitively coupled.
Yeah, I don't know how they get
Yeah, I don't know how they get that either. It is in a vacuum tube one, not in a solid state one, so that's probably where it comes from.
And then the Hartley one was, what did you say for that one, sorry?
Hartley one is tapped coil or tapped inductor.
Okay.
That makes sense? And Colpitts was capacitive divider. In other words, those two capacitors. Okay. The Colpitts oscillator is probably the mainstay of what you see in RF. And the reasons is it's a very, very stable circuit. Okay. And what else is there to say about it? Those two tapped capacitors in a Colpitts oscillator, they need to be very, very good, stable capacitors. If they change their capacitance value over time, temperature, relative humidity and stuff like that, the feedback network on the oscillator will change, and that's not a nice thing. Crystals don't like change. Crystals like to sit in their little environment and do their thing and not be bothered by changes. So the Colpitts is probably the most universally used one that you see if you're looking through schematic diagrams of radios. And those two capacitors, that C1 and C2, that capacitive divided network, are usually very, very high grade, very expensive capacitors, and the best capacitors for RF are what we call silver mica. So remember, a capacitor is two plates, two conductors with a insulator or a dielectric in between. Well, silver mica is two sheets of silver, and we're talking, yeah, the real thing, silver. And the dielectric is mica, which is a rock, it's a mineral. Okay? Silver mica capacitors are the lowest loss, the most temperature stable, the best overall at high frequencies for RF, and they're expensive. They're $25 to $30 for a single tiny little one. Okay, but in the case of building a master oscillator, where cost is no object, typically the capacitors used in there will be silver mica capacitors because that's a question on the exam. The capacitive divider in a Colpitts oscillator typically uses blank capacitors, and the answer is silver mica. Yeah. You won't find that one in the book, by the way. I couldn't find a reference to that anywhere. So that's one of those. I have it written down as NR, no reference. So, but one of the questions that hangs on in the question bank for whatever reason.
I always thought those polystyrene ones were the more stable. I'm surprised they say silver mica.
Yeah, well, some of this stuff is old.
Oh no, it's in the first page.
It is.
So,
Page
so
7-1.
Sorry, I just had it. It's the second paragraph from the bottom. It says to ensure highly stable frequencies under varying environmental conditions, oscillators are constructed using extremely stable components such as silver.
Oh, excellent. I got that one.
No reference, my blood.
Puzzle,
Page 7-1.
Puzzle.
Well, I didn't read the whole book. Okay, I'm gonna add that. Hang on. 7-1.
You're gonna be our policy guy.
Well, that's the second one we found. Perry found one yesterday, so no, that's great because I update my little guide here with it, and the next poor person who teaches this course will have that reference from now on. Okay, good enough. We're going to leave the general discussion of oscillators behind. So now we know how to generate RF, right? And by the way, modern radios, it's all generated by a computer. But still, the fundamental crystal that's driving that computer is still an oscillator, a crystal oscillator, right? That makes sense? So the next chapter in the book is receivers, and we're going to skip it and we're going to transmitters. Because unless you transmit something, there's no use having a receiver, is there?
Wow.
Oh, of course you can.
Yeah. So I just like to do transmitters before receivers. It's just me. It probably doesn't really matter, but we're going to jump to chapter 9 and talk about transmitters. And so, what's a transmitter? It's a box that puts out RF. Okay, and in simple terms. However, there's some things that we should talk a little bit more in depth about this box. We want it to be stable. What is stability? When we tune it to a specific frequency, we want it to be on that frequency and stay there. We don't want it drifting up and down and stuff like that. So stability, it's got to maintain accurate frequency. Something called spectral purity. When we transmit on one frequency, hopefully that's all we're transmitting on one frequency. We don't want the second, third harmonic, fourth harmonic. We don't want spurious transmissions from, amplifiers that turn into oscillators, and all that kind of stuff. So spectral purity is kind of the name that you want to put out only the RF that we desire. We don't want any more. So. Noise and spectral purity kind of go hand in hand. Noise is more things like power supplies. If our power supply is inadequate, we may hear some 120 hertz or 60 hertz hum on our signal. We don't like that. Got to beef up your power supply, stuff like that. We haven't talked much about modulation yet. We're going to talk about AM and FM and single sideband and all those modulation techniques. We want to make sure that we're not over-modulating our transmitters. So that. And finally, bandwidth limitations. Our guys at Industry Canada, or whatever they call themselves this week, as you probably all know, we're not told what mode we can run on what frequency on the HF bands. They say you can run from 14 to 14.35 megahertz as long as your bandwidth doesn't exceed 6 kilohertz. That's what our rules and regulations say. It doesn't say you can only run CW here and voice there and data there and that stuff. That's a US crap.
So that band plan that's out there, that's just
a gentleman's agreement and a handshake. Now, for example, in the US, they do. It is their law. You shall run CW here. You shall run voice here. You shall run data there. Here, we have no such laws. Our laws are, there's your band, maintain 6 kilohertz or less of bandwidth. That's it. Okay. So one of the things we want to do is we want to make sure that we're within that bandwidth limitation. Now, voice uses about 2.83 kilohertz of bandwidth. So if we're speaking voice in that particular band, no problem at all. But some data modes, high-speed data modes, use quite a bit more bandwidth. So we have to watch. So these guys that have HF D-star repeaters, and they're talking on 20 meters in Canada, nope. That breaks our regulations. That's more than 6 kilohertz of bandwidth. You can do it on 10 meters, because we're allowed to think 30 kilohertz on 10 meters, but not any other of the HF bands. However, in the US, they can, because they're not limited by bandwidth, they're limited by mode. So as long as they run their HFD star in the digital portion of their bands, they're fine. In Canada, we're limited by the bandwidth of the signal as opposed to the mode of the signal. So a little bit different going back and forth.
So that band plan on rack is not what the paper's written on?
That band plan on rack is written because just to the south of us, we have 300 million people, and some of them are hams, and they have to follow their rules, and they think the rest of the world has to follow their rules too. But if you go read our rules and regulations, there is nothing anywhere that says you must run CW here and you must run voice there. And none of that. That doesn't exist in Canada. We actually have some of the most lax amateur radio regulations in the world. We're pretty lucky here. So, and it pisses the US guys off to no end, because you and I can sit in the CW portion of 20 meters and talk phone all day long, and those guys are on there screaming, "You're in the CW portion of the band, get off, get off." Yeah, so, no, to be nice neighbors and stuff, you respect their band plan, but there's no rule that says.
So,
Yeah.
Just say sorry.
Yeah. Too bad. The 40 meter Aurora net, which happens, what is 7 nights a week? The Aurora net on, what is it, 7050? 7050 is CW only in the U.S. And every night they hear this voice net and it drives them nuts. But they do, a lot of them check in, but they can only check in on CW.
Where's the Aurora net based out of here?
Yeah, it's all over Western Canada. Net control
I don't,
goes
it
around.
floats around.
Yeah. It's at about, I think it's about 5:30 or 6 p.m. our time on 7050, 40 meter. But it just turns out that that's one of them that, for Canada, we can talk voice anywhere, but in the US, 7050 is CW only. So the US stations that check into that net are checking in via CW. So it's just, anyways, that's my discussion of bandwidth limitations. So in Canada, we do have bandwidth limitations. It's something to keep in mind.
And that's 6. You said 6.
6 kilohertz, yeah. Well, you can go to, what is it, RIC 4 or RIC 3 or, that was back in the basic where you had to know all that. But those documents that Industry Canada or whatever they call themselves put up now, there's a chart in there that says, here's the Canadian amateur radio bands, and all it says is you go from this frequency to this frequency and your maximum bandwidth can be X amount of kilohertz. And that's all. That's all it says. There's nothing there that you have to run CW or you have to run voice or you have to run data. There's nothing like that at all. So it's reasonably straightforward.
So they didn't really outlaw AM.
No. AM is still, there's haven't you heard the SPAM net, the Society for Preservation of AM?
No.
On 40 meters, it's just the most hilarious thing you've ever, because the net control runs AM, everybody checking in runs AM, but of course you always get a newcomer that comes across the frequency and checks in on single sideband and say, yeah, there's a really strong carrier right beside your signal, but I notched it out. So the net controllers that run that net, they know, and they have single sideband receivers set up too for people like that. But no, AM is still alive. There's nothing wrong with it. As long as you don't exceed the bandwidth that Industry Canada lays out, you can run AM. So and 6 kilohertz is just fine. All our HF bands we can run AM. That's 2-3 kilohertz sidebands. That's more than we need. So okay, we're gonna start with transmitters. Once again, I'm kind of gonna jump around a little bit here, and
You gonna follow the block diagram, oscillators first?
yeah, well, sort of like that. So, transmitters. Okay, before we actually start talking about CW transmitters and single sideband transmitters and AM and FM transmitters, we're still going to talk about the transmitter as kind of a black box in general right now. And we can consider it a black box that we put a signal into, whether the signal is a voice, a microphone, or a CW key, or in the case of digital modes, it might be a sound card on a computer, or whatever that input is. And of course, it puts out RF on the desired frequency. Some general things for the transmitters, and these I just kind of threw in because they're general and they're not really applying to anything. When servicing the power amplifier on a VHF transmitter, replace the shielding. It's a question on the exam. Yeah.
Replace?
Yeah. So when servicing a VHF, so we're talking maybe a 2-meter power amplifier, so in other words we have VHF stuff around, make sure you replace the shielding on the amplifier.
Like put it back.
Put it back, yeah.
Ah,
Well, assuming you've had to open the shielding to replace a component in there, put it back.
Yeah.
And that is just a safety thing.
Yeah.
We don't want radiating people.
Is that a question, or is that?
That's one of the questions on the exam, and no, I could find no reference to it in the book. Maybe somebody else can.
Amplifiers, I already saw it.
Did you?
I'll get you a page.
Oh,
Shouldn't they
geez.
say reinstall? Because.
Yeah, reinstall, replace.
It's like a cylinder
Sounds
handle
like
on
a
a
new one.
quad. That's a
Yeah.
nice cylinder handle.
Yeah, some of this is probably in the transmitter stuff, but I'll just go over this. Harmonics in the early transmitter stages can be reduced by using tuned circuit coupling between stages. So what they're saying is you have an oscillator, and we already talked about oscillators and how crystal oscillators, for example, can actually go at harmonic frequencies of each other. So to avoid that, to make sure we want to keep on that desired frequency, when we connect that oscillator to the next stage in our chain, an amplifier, we can put a filter in there. So we're going to use a tuned filter at every stage just to keep everything pure.
That note is on page 4-2.
Yep, see, he's found them. There you go.
Wow.
Yep. Okay. What does the neutralization circuit in the transmitter do? It cancels the effect of positive feedback, eliminates oscillations. We talked at some length about neutralization already. Okay. Oh yeah, neutralization in vacuum tube amps cancels oscillation caused by interelectrode capacitance. I think I already said that one. Parasitic oscillations are usually caused by, and the answer is accidental resonant frequencies in the power amplifier. So once again, this is just a bunch of general questions that I grabbed that don't really apply to any one transmitter, but kind of apply to them all. Parasitics, which is an undesired oscillation, usually happen in RF power stages. And once again, the reason is there's an awful lot of RF floating around, so a little short piece of wire can actually turn into a pretty good antenna and cause problems. And finally, parasitic oscillations are caused by a lack of neutralization. So this whole thing about neutralization, parasitic oscillations, there's a number of questions on them, and they kind of ask the same thing in a circular fashion. You know, they're asking the same question 3 or 4 times with slightly different wording, like parasitics usually happen in RF power output stations. Parasitics are usually due to accidental resonant frequencies in the power amplifier. Parasitic oscillations are usually caused by lack of neutralization. Neutralization is, bypassing these things and whatnot, so it's kind of a circular question. So isn't that just the most fun you've ever had? Okay, so you're gonna make the call? You're gonna make the call?
Yeah, it's getting close. It's after 11. They open at 11, so
Yeah,
I think. So
okay.
I'll go.
Okay, well, we'll sit for 45 seconds and let Perry make a call.
No, you continue.
Okay, I'll continue.
Yeah.
Okay.
It's all in the book.
It's all in the book, yeah.
If you have somebody that finds it.
Yeah. Okay, so we're gonna jump to chapter 9, page 9-9, and well, actually page 9-10.
9-10 says.
We're going to talk about the CW transmitter. The simplest way, we have an oscillator, we have a power amplifier, we can put stuff on the air. How do we actually add intelligence, quote unquote, to what we're putting on the air? So we're going to talk modulation. And the simplest thing to do is simply turn the transmitter on and off at a predetermined sequence, i.e. Morse code. That's all you're doing, is you're turning the transmitter on for a short time, or maybe a long time, and off in a certain sequence. And if somebody else knows that sequence, well, then they can obviously, make out what you're sending. So CW starts as the very simplest of all transmitters.
Why was it originally called CW? Like continuous wave?
Continuous wave.
Where did
That means when you push the button, you're just putting out a continuous stream of RF.
Oh,
You
okay.
interrupt it.
And you're it's actually interrupted wave. It should be IW, not CW, but
Okay.
yeah.
When you tune it, you're supposed to tune it on a constant wave.
Yeah, something like that.
Well, I thought it was carrier wave.
Carrier wave, constant wave.
I think it goes back to the old spark gap transmitter.
Yeah, they used to throw the
But
blade
you
in.
can't talk about a spark gap as a continuous wave because it threw harmonics everywhere.
Yeah, it's horrible
I think
things.
that's why they came up with it.
So a CW amplifier, there's a little block diagram right at the top of page 9-10 where they basically say this transmitter is an oscillator, a buffer, an amplifier, and a matching network going to the output. Oscillators we just beat to death. Oscillator, as we know, is a positive feedback amplifier with a frequency determining element, usually a crystal, to determine what frequency we go through. A buffer is just a small amplifier to isolate that oscillator, because once again, crystal oscillators like to be in their own world. They don't want to see heavy loads and power supplies varying and all that kind of stuff. So we put a buffer amplifier in there. Buffer amplifier is actually optional. There's many, many simple QRP transmitter designs that are just oscillator amplifier done, no buffer. But good idea to put a buffer in there. Lets our oscillator run nice and clean and free and no encumbrances. Then we amplify that because we want to put out a little bit of power, you know, more than a couple of milliwatts that would come out of a little small signal transistor. So we can amplify that up to, well, if we use our grounded grid configuration and 3CX 25,000, well, 25 kilowatts, no problem. You know, how much power do we want? But we amplify it. The amplifier may be one single tube. It may be a series of transistors. It may be dozens of devices, but it's just a block. We're going to amplify it. We need to match that typically to our 50 ohm antennas. If you throw up a wire in the air, it may not be 50 ohms. It may be some weird thing like 300 ohms. But in any case, we need to, for achieve maximum power transfer, we need to match our transmitter output impedance to the antenna input impedance. So there's usually some kind of matching network. All modern, shall we say, commercial HF transmitters have internal networks that match that antenna connector to 50 ohms. Okay. In the good old days, when you bought a transmitter, they weren't internally matched to 50 ohms. They actually had knobs on the front that you can tune your antenna. So instead of going out and buying that expensive ATU option, which we do nowadays, back in the old days, it was right there. You just tuned the knobs to tune your antenna. So. Okay, so that's the block diagram of it, of a CW transmitter. It's just basically an oscillator and an amplifier. And we're going to look at the schematic diagram of the two-stage CW transmitter down near the bottom of page 9-10 there, figure 911. And figure 911, as you can see, is on the left-hand part of it, it's even labeled OSC oscillator, so that Q1, that transistor, is an oscillator. And we can see that the positive feedback path is going through a crystal. You see a crystal going between the collector circuit and the base of that, so that crystal is our frequency determining element. There's a little trimmer capacitor C2 there that's got an arrow through it. That means that's a variable capacitor. So that C2 lets us swing that crystal frequency just a little bit. You can't move crystals far, like plus or minus 1 kilohertz maybe. So you order the crystal cut to the frequency you want, and depending on the temperature and other conditions, you can actually pull it up and down from that frequency by a little bit. So that's what C2 does. And notice that we have a transformer. That T1 is basically, it's an RF transformer that couples the oscillator stage to the amplifier stage. The amplifier stage is Q2. And they very nicely even labeled it. They said it's a Class C amplifier. And if we remember, what that meant was that Class C amplifier doesn't even turn on until it gets about 0.6 of a volt on the base there. And then it only amplifies for the positive half of the cycle, and it does nothing. It cuts itself off and sits there like a bump on a log for the negative part of the cycle. So it actually puts out a pretty nasty looking, square, horrible looking waveform. It's nothing at all like a nice clean sine wave. And it goes through that T2 with the matching C5, which that T2 is the impedance matching to match it to, say, 50 ohms for antenna. And then that block FL1, guess what? That's a low-pass filter. Because once again, these Class C amplifiers are putting out an awful lot of harmonics, an awful lot of extra stuff we want to get rid of. So that FL1 is typically a bunch of coils and caps in a configuration. So we filter off at the second harmonic and anything higher. So it's a low-pass filter. Right? So if somebody shows you a picture of an oscillator in a Class C amp, you all know that it's a two-stage CW transmitter, right?
rates.
That's a question on the exam, believe it or not.
You say that again?
An oscillator and a Class C amplifier are constituent components of a two-stage CW transmitter. Okay. Why is the oscillator and the amplifier coupled by an RF transformer? Yeah. Well,
Isolate currents?
Or to isolate oscillator.
okay. Well, isolation is part of it, yes. Yes, absolutely. And the other part of it is on the primary side of that T1, T1, C2 actually make a tuned network. So we're actually doing a little bit of filtering too. Okay? Okay. So on the output of our Q2, our Class C amplifier, okay, it goes through a tapped inductor. You see that tapped inductor, that T2, all right? And down below there, you see RFC2, and you see C6 and C7 and all that kind of stuff. What's all that?
Choke for filters.
Yeah. So it's an RF blocker for the power supply. But wouldn't those capacitors just take all your RF and sewer it to ground? Isn't that cool? So that's power supply bypassing down there. Okay. And, okay. What is the what is the transistor in the second, what is the function of the transistor in the second stage of a two-stage CW transmitter? So, in other words, what does the transistor in the second stage do? It's a power amplifier. Yep, that's a question on the exam. What is the function of the transmitter in the second stage of a two-stage CW transmitter? That's the question.
So Q2 we're talking.
We're talking Q2, and the answer is it's the power amplifier. Okay. Out of the four answers they give you, the right one is power amplifier. See? Okay. Going back to the block diagram and ignoring that little schematic, the block diagram back at the top of the page where we had oscillator, buffer, amplifier matching. In a well-designed transmitter, once again, we want to leave that oscillator alone, and that's why we put that buffer amplifier in there. However, that little schematic down below, we don't really have a buffer. We're going straight from the oscillator to the PA with no buffer. All the modern radios and better designed CW transmitters do have a buffer in them, so there's another little stage just after the oscillator before it goes to the power amplifier, and that's just once again to provide some isolation to let the oscillator sit there and do its own thing. Your key that you plug in to turn the darn thing on and off, down in this particular schematic diagram, if you look on the very bottom where it says figure 911, just before the words fig 911, that's the key. Okay? And notice what the key is doing is, you see the little plus sign there? The key is actually applying power to the oscillator. So when you key, that's like a power switch. When you key down, you're turning on the oscillator. And when you key up, of course, the power is removed, so the oscillator dies. Okay? That's a really bad way to do things, because once again, oscillators like to sit there running dumb, fat, and happy. They don't like to be switched on and off and stuff like that. So the keying in a well-designed CW transmitter is actually done not in the oscillator stage like it is here, but it's done in a buffer stage. So they add one more buffer amplifier, and it could be a single transistor or it could be a single FET, Could be a single vacuum tube, or it could be a modern integrated operational amplifier, but there's another buffer amplifier, and the key is actually turning on and off that amplifier and leaving the oscillator alone. Okay? So pretty much all the modern HF rigs, and even a lot of the kits that you can buy these 40-meter CW transmitter kits that put together, they almost all will actually key a buffer stage, not the oscillator. That being said, you can build this circuit, no problem. You have your advanced, you can build a transmitter. Isn't that just the most fun? Okay. Next off is AM, ancient mode. So we've got this transmitter that we can put out RF. One way that we can modulate this RF is to simply turn it on and off, CW. Turn it on and off in a specific sequence, and as long as somebody else knows the sequence, well, they can understand our transmissions. Along came AM, ancient mode. Okay. And what ancient mode does is we can turn on this transmitter while we have basically an RF signal coming out of it. We know that we can turn the RF signal on and off. That's one way to modulate it. Another way to modulate it is, instead of turning it on and off, let it stay on continuously, but change its amplitude or its size or its voltage, if you like. Okay? And if we can change its amplitude in a prescribed format and detect those changes at the other end, we can now do things like voice. Okay? Isn't this just the most interesting thing? So what we do is, in the case we'll talk about a voice transmitter, is we have an oscillator with a buffer and a power amplifier. And on the power amplifier, we do some trickery. Okay? The power amplifier is there, it's putting out however many watts, 100 watts for a typical HF transmitter, stuff like that. And it's drawing power from a power supply. We also have a microphone that plugs into the front of our radio, and it goes through a little audio amplifier that amplifies our audio from the few millivolts that comes out of a microphone up to a pretty reasonable amount. And then we go through another audio power amplifier that can put out lots of oomph. And a 100-watt audio power amplifier is nothing. Like, you know, anybody that has a stereo sitting in their living room has, you know, probably close to a 100-watt power amplifier. It's not high-tech or anything. But instead of hooking this up to a loudspeaker and hearing our audio, although the sound of our own voice might be wonderful, but that's really not the intent, we take the output of that power amplifier and we connect it directly to the power supply of our RF PA. And everybody goes, huh? What the hell are you talking about? So the RF power amplifier, assuming it has a stable power supply, is putting out a nice clean CW, nice clean RF signal. If we take the power supply for that power amplifier stage and we start changing its voltage up and down, so we can turn the power supply right off, well, you're going to get no RF. If you turn the power supply up to, say, double its level, well, the amplitude of your RF waveform is going to go up. So if we can change the power supply voltage, we are effectively changing the amplitude of our waveform. And that's all we're doing is we're taking our microphone, we're going into a powerful audio amplifier, and the output of that amplifier we hook directly to the power supply of the PA. Sounds kind of counterintuitive. But then when we speak into the microphone and our voice gets loud, we're actually going to be adding voltage to the power supply. And likewise, when we're not speaking, we're adding zero to the power supply, so it's just going to be carrier only. And so what we've done is now we've kind of imprinted, if you will, our audio onto this wave. So the actual RF, which may be at, let's say 630 kilohertz, it's just RF, it's just CW, it's nothing. Okay? What we've done is we've taken and we've changed its amplitude or the size of it in according to our voice when we speak into the microphone. When we speak loudly into the microphone, it changes it a lot. When we are silent or we speak very softly into the microphone, it changes it only a little bit. If we have no modulating audio at all, the carrier stays constant. Okay? And that's what AM is. Amplitude modulation is what AM stands for. It also stands for ancient mode. Okay. And the fun part about that is the carrier part of it, in the case of 630 kilohertz, doesn't have any information on it, because it's just that. It's the audio that we've imprinted on there that's the important part. Okay. And we still got time before the pizza gets here, right? Okay. So what we're doing is we're looking at the modulation. That's the word I'm looking for. Yeah, that's totally it. The carrier is useless to us, but the audio modulation is useful. Okay, and what we want to do is we want to get rid of the carrier because it's useless, but we're interested in the sidebands, the things that are left. And I really haven't talked about the frequencies and the sums and the differences and the sidebands and stuff. And so I'm going to kind of break away from the discussion and go back to that. So what's happening is by modulating the power supply of our transmitter, we are mathematically multiplying our audio waveform with the RF waveform. It's actually it's a mathematical multiplication that's doing it. It's a simple concept to say, oh, all we're doing is just changing the power supply, but in reality, it's a multiplication. And when you multiply any two frequencies, you get the sums and the differences and the originals back. Just as we talked yesterday when we talked about mixers. Okay, mixer, multiplier, same thing. So in the case of our voice, we're talking frequencies in the order of 1 kilohertz, which is a nice whistle if you can whistle. Yeah, that's, I don't know if that's a kilohertz, but stuff like that. So our audio is down in the audio range, in say the 1 kilohertz range. Our RF, of course, is in the RF range. Maybe it's 630 kilohertz or whatever your favorite station is. Okay, we're mixing those two together, and the way we did it was to use the audio amp to modulate the power supply, but it ends up it's mixing. Okay, and so when we mix 1 kilohertz whistle, because we're whistling into our microphone, and that 630 kilohertz carrier, we get 1 kilohertz. That's one of the originals. We get 630 kilohertz. That's one of the originals. And we get 631 kilohertz. Add the two together. And we get 629 kilohertz. Subtract the two, because we get the sums, the differences, and the originals. So 2 frequencies in gives us 4 frequencies out. Okay. We're not interested in the 1 kilohertz audio because that's not even RF, it's just audio. So we just ignore it. That's what we have filtering for. It's gone, okay? The 630 kilohertz, that carrier, is just that. It's a carrier. There's nothing on it. The intelligence, so to speak, or our audio is on the 629 and the 631, which is the lower and the upper sideband. Okay? And for the longest time, AM was the mode. And some ham radio guy sat down and looked at this and said, this AM is really inefficient because half of your transmitter power is making that carrier, and then a quarter of your transmitter power is making each sideband. So half of your transmitter power is doing nothing. It's not transmitting your voice. Okay? Only a quarter of your transmitter power goes into each sideband, and half goes into the carrier. So this ham radio guy said, all we really need is these 2 sidebands. We don't need the carrier. And if we can get rid of the carrier, well, now you can have 50% of your power in each sideband, and you effectively can transmit farther. So what this character did was he came up with something called a balanced modulator. And all that is a mixer, but it's a mixer that only gives you the sums and differences, and it gets rid of the originals completely. So once again, if we have our 1 kilohertz audio, and we have our 630 kilohertz RF, and we go into a balanced mixer, all we get out is 631 kilohertz and 629 kilohertz. The carrier is gone. Okay, so he did some magic. He built a circuit to do that, and it's called a balanced modulator. okay, our balanced mixer. Okay, so it's just a special circuit of a mixer is what he did to do this. And now 50% of our power is in each of those sidebands. So now we're running a brand new mode called double sideband suppressed carrier. We have two sidebands but no carrier. So it's DBSC, double sideband DSSC, double sideband suppressed carrier, okay, DSSC, okay. And then, of course, they got even smarter and they said, well, really, we don't need two sidebands, we only need one of them, right? You only need the upper one or the lower one, it doesn't matter which, they both have the same information on them, right? So what he did was he took this balanced modulator and he simply put it into a filter, either a high-pass filter or a low-pass filter. And on our modern HF radios, it's typically just a push button. One says USB, one says LSB. And all you're doing is you're picking one of those two sidebands and letting it go out the transmitter. But now 100% of your transmitter power can go into that sideband, okay? Instead of back in the ancient mode days, half your power was gone in a carrier that was useless, and a quarter was left in each sideband. So we've effectively gone 4 times the amount of power into that sideband, and we really haven't changed anything about our transmitter. We still have a 100-watt transmitter. But instead of putting 50 watts into a carrier and 25 watts into each sideband, by getting rid of the carrier, filtering off one of the sidebands, we now can put the full 100 watts into one sideband. Make sense?
Do they generate usually one or the other? Or one
They
or the
usually generate both, and internal filters pick which one you want.
other? Oh.
Balanced modulator still generates both sidebands all the time. But this is filtered at a very early stage in the transmitter before we get to the power amplifiers and all that kind of stuff. So the technique of taking an audio power amplifier and plugging it into the power supply or your PA, that is not used. Well, actually, I shouldn't say it's not used. It's still used in very high power broadcast transmitters, like the 50 kilowatt transmitter that you were at the other day. That actually uses that technique. The audio is amplified really big and plugs into the power supply of the PAs. That's about the only place it's used. We do all this at a low power circuit well before we start amplifying and doing all that kind of stuff. And it's simply because it's cheaper to do it down there. Low power components are cheap. They don't generate much heat. They're easier to work with, easier to design. They're available in mass quantities. It's a economy, economy of scale, they call it, or whatever. So, that make any sense? So, single sideband is really AM just chopped to pieces. Okay, so it all comes back to AM, and it all comes back to multiplying frequencies. We're just taking an audio frequency, multiplying it with an RF frequency. We end up with the sums and differences. Some genius ham came up with this balanced modulator that gets rid of the originals, so we only get the sidebands. Well, now we can pluck off that one sideband, whether it's the upper or lower, doesn't matter, they're identical. They're actually 180 degrees, they're phase shifted with each other, but they're identical, so you only need one and off you go. And so the convention in amateur radio that we use typically is in the HF bands. If you're above 10 megahertz, we usually pick the upper sideband. If you're below 10 megahertz, we pick the lower sideband. That, once again, is just a gentleman's agreement. There's no hard and fast laws or rules that say you must use lower sideband on this band. Not that way at all. We just do that because, confuse people. Hopefully that makes some lovely sense. Okay, so after that big long discussion, going from an AM transmitter to a single sideband transmitter effectively has given us 4 times the output power. Okay, now we're going to throw technical numbers at you. If I told you 4 times the output power is 6 dB, you'll believe it, right? Okay, so decibels is just a mathematical ratio, a dB. And when I say dB, it means nothing. It's just a numerical ratio. You have to talk about decibels in context. So when we talk about power output levels, which I was just speaking about power output of the transmitter, for decibels in power, every 3 decibels doubles your power. Okay, so if you're on 100 watts, and you go buy a 200 watt transmitter, you've increased your output power by 3 dB. You've doubled your power. Okay, another doubling of power, so from 200 to 400 is another dB. So that's 6 dB. Okay, another doubling is just another 3 dB. Okay, so decibels and stuff. And we'll be talking more about decibels when we get into talk about antenna and antenna gains and whatnot, but used everywhere. You read specifications, you'll see dBs everywhere. And the key is, if you see dB alone and there's no reference to what it's talking about, like power or voltage or something like that, it's meaningless because it's just a number, it's a ratio. So you have to know what the context is. And because of that, in mathematical terms, we usually put dB and then a trailing letter on the end of it. Like, for example, dBW means dBs with respect to 1 watt. So when you see dBW, you know, okay, this guy's talking about power ratios and stuff like that. If you're talking about voltages, this is where things get really interesting. A doubling of the voltage is 6 dB. Double of the power is 3, but double the voltage is 6. Okay? And I mean, that's not such a bad thing, but unfortunately in radios, when we talk about transmitters, we talk about power. The power output of my transmitter is 5 watts, 10 watts, 100 watts, 1,000 watts, whatever it is, but we talk about power. So when we talk about transmitters, the ratios we're using is dBs, and 3 dB is the doubling. In receivers, on the other hand, we talk about the voltage on the center pin of the antenna jack. We're talking about the voltage of the signal we're receiving, and that's what an S meter indicates, is the voltage on there. Okay, so for receiving, a signal that is twice the voltage is 6 dB higher. But in transmitting, a signal that's twice the power is 3 dB higher. Okay, so 1 S meter is 6 dB, which is double the voltage, which is 4 times the power.
So when you're saying 1 S meter, you're talking
When one S unit, say the difference,
One S unit.
one S unit, say the difference from S1 to S2 is 6 dB. It's double the voltage on your antenna connector. 6 dB happens to be 4 times the power. So if you have a 100 watt transmitter and you're talking to your buddy over a good HF path and you're S5, you have to go buy a 400 watt transmitter to be S6. Yeah, just think of that. So to be S9, how big does your transmitter have to be? Okay, yeah, it's huge. So these guys that have a 100 watt transmitter and a 1,000 watt linear, well, the 1,000 watt linear over 100 watts, that ratio happens to be 10 dB. Okay, well, 6 dB is 1 S unit. 10 dB is what, 1.5 S units? So the difference between going from 100 watts to 1,000 watts, all things being equal, is 1.5, 1 3/4 S units.
So what you're telling me is.
So is it worth investing $4,000 in that amplifier and stuff? You know, to each their own. I'm not saying it's not worth it, but in the end, it's, yeah. But there's always the situation that you may be S0, you might be lost in the noise. You turn that thing on, well, now you're S1. Now they can hear you. Is it worth it for that?
Location.
Yeah, that's, you know. But yeah, so you know, when you start talking output power transmitters and when you put it into perspective, into dBs and convert that to S units and stuff, you see that running an awful lot of power is not necessarily a big advantage. You have to run humongous amounts of powers, like in the tens of kilowatts, to really make a difference. So, which of course, none of us can afford the power bill to run that high, so isn't that just the most fun? The balanced modulator produces double sideband suppressed carrier. I think I tried to stumble over that one. That is a question on the exam. Okay. Where is the carrier suppressed in a single sideband transmitter? And the answer is in the balanced modulator stage. Okay. By the way, this thing doesn't completely get rid of the carrier. It suppresses it. It doesn't eliminate it. There is still a weeny bit of carrier left behind, unless you're using new DSP techniques, which we won't talk about right now. So there is a standard that Industry Canada and the governments of the world have set out, saying if you want to call your transmitter a single sideband transmitter, it must have at least 40, here's this dBs again, 40 dB, that's 40 dB of carrier suppression. So what the hell is 40 dB? Well, if you have a 100-watt transmitter, okay, 40 dBs is 4 decimal places. So that would be 1 decimal place would make a 100-watt transmitter 10 watts. Another one would make it 1 watt. Another one would make it 0.1 of a watt. Another one would make it 0.01 of a watt. So that carrier frequency coming out of the arse end of your 100-watt transmitter can be no more than 0.01 watts to be within spec. Okay? And if you pick up the specifications for any modern HF transceiver, they will say single sideband carrier suppression, and they will have a number, and hopefully they say at least minus 40 dB, because minus 40 is what both the FCC and Industry Canada says if you want to run a radio on the single sideband. Okay. A single sideband phone signal is produced by a balanced modulator followed by a filter. So remember, the balanced modulator is the thing that gets rid of the carrier, gives us the 2 sidebands, and the filter lets us pick either the upper or lower sideband. To test the power output of a single sideband transmitter, I referred to this very briefly yesterday when we were talking about things. But the standard test, because single sideband transmitters only put out power when you speak into the microphone or when you modulate them. When you key down and there's no audio, they don't put out any power. So how do you measure the stinking power output, okay? And the standard way to do it is to put in what they call a 2-tone test. It's 2 audio tones that are not harmonically related. So in other words, it's not 500 hertz and 1 kilohertz, because those are harmonics of one another. Typically it's like 1100 hertz and 1250 hertz or something. You put these 2 tones in, you crank it up, and you measure the peak envelope power, or the PEP of that thing. So they call that a 2-tone test. So if you ever hear of an RF 2-tone test, that's somebody testing a single sideband transmitter. The 2-tone test, of course, shows you the peak output power, the PEP, peak envelope power, is what single sideband is measured in. And it also, shows you that you're not, distorting badly, clipping and flat topping and all that kind of stuff. The neat thing about the 2-tone test is the peak output power is twice the power of any one of the tones.
What?
Yeah. What did he say?
Say again?
Well, let's just assume you're putting 1 tone, a whistle, into your single sideband transmitter. You can very simply measure the peak and say, fine, that's the peak output of my transmitter. But now when you put 2 tones in, which peak do you measure? Do you measure the peak of the 1 tone or the 2nd tone? And it turns out it doesn't matter which one you measure. You can measure one and just simply double it, and that's your peak output power. Cool, eh? If you turn up...
He's got the wires here, everybody's like, okay.
Yeah, okay. Tolerate it.
Take your word for it.
Okay, so.
If you turn your microphone gain up too high,
Yes, Steve.
so your audio is now being clipped by a limiter inside there, you get something called flat topping. In other words, your waveform comes up, and instead of being a nice waveform, it gets clipped off. It gets flat tops, okay? So that flat topping is caused by excessive drive. Your mic gain is too high. Or maybe some coupling stage inside your transmitter has gone nuts and is overdriving something. So, to keep a nice high output level on single sideband, there's all kinds of tricks. One of the modern tricks is to use a speech compressor. Because human speech, as we know, is very dynamic. When I'm not speaking, just the gap between my words, there's zero energy. In the case of a single side transmitter, that means zero output power. But on the louder portions of my voice, on the peaks of my voice, it's quite loud. It's very dynamic. And if we want a good punchy signal that people can hear, we want our transmitter to put out lots of power, what we can do is we can compress the dynamic range of our voice. In other words, all compression does is it takes the louder portions of our voice and makes it quieter. And so all I'm doing is, instead of a dynamic range from silence down here to the peak of my voice up there, I'm going to take those peaks and I'm going to compress them and make it this big, and then I can take the whole thing and slide it up. And overall, my voice will be louder. Okay? And to a certain extent, that is almost inaudible. It doesn't affect the fidelity of the speech much at all. So compression, and all modern HF rigs have some kind of speech compression adjustment. It may be in a menu, or it may be a dial or something, can do that, and that helps you keep the dynamic range of your voice within a nice band of levels, and then you can put that out and try and keep your output power as high as you possibly can, even though you may speak quietly. Okay? And the fancier HF rigs will take this compressor and add an expander to it to make something called a compander, which also says when you speak quietly, it will actually amplify your voice up. When you speak loudly, it will bring your voice down. So we're taking this really wide from silence to the peak of your voice, and we're going like squish, like that, and now we can take that squish and put it out at full power. Okay? So it gives you a real punchy signal to get through, because power equals distance equals DX contacts, right? So guys spend tens of thousands of dollars on fancy microphone processing gear that Mr. Bob Heil has made millions of dollars off of to do this. So they have that real punchy, clear sound on HF, and they can break through those pile-ups and get those rare contacts. And like I say, people like Mr. Bob Heil have made a very good living off selling that audio processing stuff. To the extent that even his headsets and microphones are specifically tuned to the voice frequency that punches through HF the best. They don't necessarily sound the best. You wouldn't use them on a sound stage or in a broadcast studio, but on an HF rig, they're great. There we are. Yep, come on. Yep, that important part. Okay, we'll just finish up here. I just got a few more things to go, and then we'll break for lunch. Perry can pay the bill, as usual. So another thing, we talked about flat topping, and that's very undesirable. Any flat topping on your audio signal is not a good thing. So all modern single sideband transmitters have something called an ALC, automatic level control, built into them. And if you read the instruction manual, some of them are a little vague, and some of them don't really explain what it does and why and stuff. But the ALC is there to prevent you from over-modulating, flat topping on your single sideband signal. So once again, it's watching the modulating signal, it's watching the RF signal, and as soon as you get close, it actually starts shutting down the amplification stages in your transmitter, so you can't over-modulate. It's called ALC. Almost every transmitter has it. They usually have a meter position. You flip to an ALC position, and you go to a dummy load or a quiet frequency, and you talk in your normal voice, and you adjust this ALC control until the needle just starts moving off the end stop. And what that is it's looking at the peaks of your voice, and it's saying, okay, above this level, that's it. You're not going any louder than that. And that ALC is setting that level there. So once again, it's a safety valve, so you don't flat top and overmodulate your transmitter. So it's not an audio compression like I talked about with the microphone audio compression. That's done in the audio part. This is done in the RF part. And because it's done in the RF part, it is ugly and it sounds really bad. And if you're running digital modes like sound card modes and your ALC is kicking in, nothing will work because it completely whacks any phase relationships and audio relationships and stuff like that. So ALC is done in the RF part, whereas mic gain and mic compression and mic EQ and stuff is all done in the audio stages. It's easy to do this stuff in audio because it's all low frequency and the technology's been with us for many, many years. It's very difficult to do that in RF. So in RF, this ALC is basically, it's the brute force brick wall saying ye shall go no farther, period. Okay? Don't want to get into ALC, so carefully check that on your single sideband transmitters. Make sure your ALC is not bouncing up into the red, which means your signals are being highly distorted. And especially if you're running digital sound card modes, you know, the many popular modes where you hook a sound card up to your HF rig now and type on a keyboard. If your ALC is active, almost none of those will work because it does highly distort the signal. So just be aware that it is built in. Every single side transmitter, good single sideband transmitter has ALCs. They are adjustable, and the manual usually tells you, flip your meter to ALC, speak in a normal voice into the microphone, and adjust the control so the needle just dances off the end stop. In other words, it's just taking effect on the very peak of your voice. If you're running digital modes, turn the damn thing off completely. Okay. Speech compression, I already talked about. Speech compression is full amplification of low-level signals and reducing amplification of high-level signals. So, once again, there's people like Mr. Bob Heil that's made tons of money off selling audio shaping circuits for your HF stuff. He does take a scientific approach. He's been in this business for many, many years. His equipment does work really well. Just don't expect it to sound good on a sound stage or a recording studio. It's not designed for that. It is designed for noisy HF single sideband voice communication. So the Heil headsets and the earphones and his processing modules that you can spend hundreds and hundreds of dollars on, they do work. You know, he took a very good scientific approach. He did a lot of research into doing that. But you know, don't use them in a recording studio. They'll sound like shit. They work really fine for what they're intended for HF voice communications. So, with that, it's 5 to noon, and so we will take our usual hour, and we'll come back and talk about FM transmitters. And everybody knows what FM stands for, right?
What?
Effin' magic. I had an instructor in electronics school that used to go, don't worry about that, it's FM. Don't worry about that, it's FM. And finally somebody asked, what does FM stand for? It's fucking magic.
This is all witchcraft.
Yeah. So, yeah, for the benefit of Todd, we take a whole hour, so we'll be back at 1.